Good morning, gentlemen. Today is Wednesday, May the 6th, and today we are going to talk a little bit more about waves. So, if you've ever been out in a boat on a rough waters, a rough lake or the ocean, you'll know that um, sometimes you can see two waves come together, all right? And when that happens, for an instant anyway, they form one big wave, right? In other words, their energy is combined. Um, and sometimes when a trough and a wave come together, they kind of neutralize each other. And that's why your boat goes up and down and up and down. It's not just necessarily one individual wave, but it might be multiple waves that are acting on you at the same time as you're sitting in your boat. This is what we call interference. And this occurs with not only mechanical waves, but also with electromagnetic waves. All right, you can have interference between radio waves and light waves and that sort of thing. All right, but we'll get into the electromagnetic stuff a little bit later on. Today, I want to concentrate more on what happens with mechanical waves as they run into each other. Okay, so when two waves travel through a medium at the same time, they each affect the medium independently. Okay, so for example, let's say here's the equilibrium, and I've got a wave moving along, and I've got another wave moving along, and this one's moving to the right, and this one's moving to the left. Well, when they come together at this midpoint somewhere, right about there, they're going to form a wave that's if this one has an amplitude of A and this one has an amplitude of A, can you guess what the amplitude of this one's going to be? All right, yeah, 2A. All right. In other words, this wave is going to be twice as high as either of these two. All right, assuming that their amplitudes are the same here. Interestingly enough, you can do just the opposite as well. Let's say you've got a wave moving toward the right with an amplitude here, and another wave moving toward the left with an amplitude here. But notice this amplitude is on the opposite side of the equilibrium point. So if this is A, this would be negative A. Can you guess what's going to happen when these two come together? Now, if we were in our classroom, I would have a drawing of this, and I do have a video at the end of this presentation that I'd like you to watch. But what happens here is, you guessed it, nothing. All right, the wave literally disappears because the one moving to the right and the one moving to the left, interfere with one another and literally cancel each other out. All right, this is what's known as interference. Okay, now interference is governed by what we call the principle of superposition. All right, and what this means is at the point at which two waves meet, the displacement of the medium is the sum of the displacements of the individual waves. And the picture that just popped up here, illustrates kind of what I tried to illustrate in the previous diagram by hand. All right, this is a little bit better. And again, I have a video hyperlinked into this PowerPoint later on toward the end. And you can actually see this, right? If we were in class and I had my big spring, I could demonstrate this. And what I typically do is have everybody take a slow motion video of the spring with a wave on the bottom and a wave on the top coming together, and you literally see they cancel out just for an instant, but they do cancel out. So anyway, this slide illustrates what I drew in the previous slide. Here we have obviously an additive effect where a wave of amplitude meets another wave of the same amplitude, and they produce, just for a minute, an instant really, a wave with twice the amplitude. Here, an amplitude of A and an amplitude of negative A come together, and just for an instant, the spring or the slinky or the string, whatever it happens to be, has no amplitude at all. It literally cancels out. Okay, so that is what we call interference. All right, and although you've already seen this, I do want to point out that we have two different kinds of interference. You have constructive interference, where you produce one big wave out of two little waves. But you also can have a scenario where you have destructive interference, right? Where in this case, you've got a wave coming here and a wave coming here. Pretend they have the same amplitudes, and the wave literally cancels right out. Okay, and again, remember, this wave is moving toward the right, and this wave is moving toward the left. This one is moving toward the right, and this one is moving toward the left. Okay, and so the top drawing is constructive interference, and the bottom drawing is destructive interference. Now, in every example that I've shown you thus far, the amplitudes of the wave have been equal, at least in magnitude, maybe not in direction, but equal in magnitude. And so either you get a wave twice as big or a wave that cancels out. In reality, waves almost never come in equal sized amplitudes unless they're being produced artificially. And so you can actually have a scenario where you've got a wave, a big wave, and a little wave coming at each other. And so let's say this has an amplitude of 2A, and this one just has an amplitude of A. Well, what's going to happen when they meet? Well, that's going to be, again, another example of constructive interference. But this time, the result is going to be, I didn't draw that very well, but it's going to have an amplitude, you guessed it, of 3A. Excuse me. Now, what if, on the other hand, rather than having them on the same side of the equilibrium point, I've got a wave with an amplitude of 2A moving this way, and a wave of amplitude negative A going this way. All right, so 2A is moving toward the right, and negative A is going toward the left. Well, in this case, when they come together, you simply add them together, right? 2A plus negative A. And right in the middle here, I'm just going to have this little teeny positive A amplitude wave, all right? You're just adding them together, all right? This is a really fun lesson in the classroom with that really big spring, because literally you can see all of this stuff with these or the slinkies and that sort of thing. And I'm very sorry that I can't show it to you, but I do have, again, there's a video at the end of this presentation, a YouTube video that I did not make, that kind of illustrates it, okay? Okay. Now, there are some properties of these waves that interfere with one another that you should be aware of, okay? When two waves with equal but opposite amplitudes, so in other words, one on the top, one on the bottom, come together and they meet, there's going to be what we call destructive interference, all right? We know all of this from the previous couple of slides. But there is one point on the medium or in the medium that remains completely undisturbed at all times. It doesn't move at all. As the two waves, the top wave and the bottom wave, come together, they literally cancel each other out, and there's one point on the spring that stays completely stationary. All right. Again, in class, I would show you this because you've got I can tie a string right in the middle of the spring, and you can see the waves are going up and down and up and down and back and forth, and the string doesn't move at all. Okay. And so if a wave is going, and I don't know that I'm going to actually be able to draw this, but whoopsie daisy. I don't know where that is. There we go. So here is the wave, and here's the wave moving in the opposite direction. Now here is the two waves when they're just coming together. I'm sorry, equal to opposite. I did this the wrong way. erase, bam, bam. Okay, let's try this again. Let's say that we have this wave going this way and this wave going this way. When they come together at this point, okay, this point right here is what we call the node. And if you watch this point, it will not move at all. Now, this is kind of hard to draw, but I'm going to draw one wave on top. I'm going to draw another wave on the bottom. Ugh. All right, but the average this point right here, right, because they were adding two waves together, but that point right there is the node, and it doesn't move. All right, tough to see and I know these drawings are awful. It's tough to see there, but it does exist. And if you've got a slinky at home, you can actually do this. Get yourself a partner and create a standing wave, and you can actually see a point on the wave that doesn't move at all. Now, the opposite of a node is an antinode or an antinode. All right. In this case, all right, when two waves with identical amplitudes meet, in other words, we have constructive interference, there will be a point in the medium that undergoes a displacement equal to the sum of the two amplitudes, a maximum displacement. All right. And I showed you this already, but you've got a wave of magnitude A and a wave of magnitude A. They come together and they form one big wave for just a minute with a magnitude of 2A. Okay, so that's A, and that's A. Now, what happens though, everything that I've drawn for you thus far is two pulses, really, in a medium. One's moving to the left, one's moving to the right, and eventually their paths cross and there's interference of some sort, whether it's constructive or destructive. What if, rather than just sending a single pulse, okay, that bounces back and forth, I actually set up a standing wave. In other words, a wave where I'm generating one wave after the other. I don't know how well you can see this, but you're generating one wave after the other, and they're reflecting back and forth, and interference is occurring all the time. Well, if that's the case, then you form what's called a standing wave, which apparently isn't going to pop up for me. There we go. All right. So what exactly is a standing wave? All right. Again, if you've got a scenario where you're sending one wave down, but you're doing so every few seconds or every second or every half a second, then you're going to end up producing a standing wave. If one end of a medium is attached to a vibrating source and the other end is attached to a fixed point, the waves are reflected. If there is no energy loss, the reflected wave will have an equal but opposite amplitude, right? We know that. This is from the lesson from yesterday. But constructive and destructive interference will occur, which will produce stationary nodes and antinodes. And what that might look like is this. Okay? Pretend this is the spring, and my hand is creating a wave of a certain frequency and therefore a certain wavelength. This represents the wall on this side. And so the reflected, notice that the original wave comes through here, but then the reflected wave is 180 degrees out of phase. Well, what that does is, if I was to represent this as the equilibrium line, this is the position of the spring without a wave in it, then at this point right here, I've got maximum amplitude back and forth and back and forth. At this point, I've got no amplitude, right? It's not moving at all. Maximum, none. Maximum, none, and so on. And so When you combine these nodes and antinodes with a constant frequency source, constant frequency vibrating source, you produce stationary nodes and antinodes, and that's what we refer to as a standing wave. This is not necessarily important in terms of ocean waves and that sort of thing, but it can be very important when you're trying to produce radio waves and things that travel through the air. Again, when we get to electromagnetic waves, we'll talk about that a little bit more. Okay. Now, here is a hyperlink to a video on this, and it actually shows, I guess it's a college professor and his poor wayward assistant, Parker, conducting this experiment. Now, I would have done this with one of you as my assistant. So when you watch this poor guy whose name is Parker, all right, just know just how dead he is inside. It's very sad. But in any event, watch this. Copy this link into your browser or whatever you have to do, and just have a look at the production of standing waves, and that'll hopefully give you a better idea of what's going on here. All right, gentlemen, happy Wednesday, and I will see you soon. Okay. I have no idea where the off button is. That's great.